All right, good afternoon, everyone. I know there's a lot to discuss, especially with the project proposals due tonight. So hopefully everybody remembers that. And we did say that there won't be any late days that you can use for submitting the project proposal. So you should definitely make sure you do it by the end of the day today. Okay. So yeah, just a reminder once again, project proposals are due tonight. Yeah. All right. One other thing was yeah, recitation. So there will be a recitation tomorrow. Zichao is going to do it, and it's going to be on support vector machines. So again, you're all encouraged to go, learn about it some more, and whatever questions you have, feel free to email those to Zichao in advance if you want him to cover anything in particular. Okay. All right. So so far in this course, we have talked a lot about classification methods, right? So we've seen many of them. We have looked at naive Bayes. That's the first one we started with. Then we looked at perceptrons, kernel perceptrons, logistic regression, support vector machines, right? Both in their primal and dual forms. And of course, you can do the dual form is the kernelized version, right? So we've talked about a lot of classification methods. So now let's turn to regression, okay? And we'll see that, yeah, we can do something similar here, at least in the sense of we were looking for maybe linear decision boundaries earlier. Now we'll talk about fitting linear functions to our data, okay, in regression. So again, there's a notion of complexity here, and kernels let you expand this complexity in the classification case, as you have seen. And at least for today, we might focus just on linear regression, but next class we'll talk about non-linear regression as well, using some kernel tricks. Okay. All right. So let's talk about linear regression. Just a reminder again. So what's classification was about taking some input and trying to predict its output, which is discrete labels. So for example, the topic of a document or the diagnosis corresponding to some cellular images. So that was classification with discrete labels. What happens if we have continuous labels? That's what we call regression, and that's what we'll focus on now. So now the goal is to, for example, do stock market prediction, where you have your input is maybe the state of the market at a particular time and so on, and you're interested in predicting what the share price might have been. Right? So again, this is a continuous quantity that you want to predict, not categorized into discrete classes, and we'll call this regression. Other examples include weather prediction, very similar to the previous one, where you're interested in predicting the temperature. Again, does not belong to specific classes, but we're interested in predicting the value up to certain accuracy. Another example would be sensor networks. You're trying to predict the value of contamination at a location based on some measurements you have made at other locations. So you take some measurements, you're trying to fit a function to your data now to try to predict the value at unobserved locations. So that's another example of regression. Okay. And we said, so these are both examples of what we call supervised learning, because your training data set consists of both inputs and you have associated outputs or label examples. And we want to be able to, given such pairs, be able to predict the label of a new example well. Right? And both classification and regression are examples of that. And the difference being, as we talked about earlier, this has discrete labels, this has continuous labels, which guides the choice of our metric. Right? For classification, what was the metric of interest? What were we aiming to optimize in classification? Yeah, number of correct labels, or actually that is the empirical version of it. You care about the probability that you get the label right. But yeah, its empirical counterpart is you just count how many you get right. So the probability of misclassification or the probability of error, right? That was the goal. And in regression, we talked about it in the very first class. What would be a good, at least one good measure of regression accuracy? Say it loudly. It's loss. Even here it's a loss function, right? This is the expected value of a loss function. Does anybody remember what loss function is used when we talk about the probability of error as being our error metric? What's the underlying loss? Binary, yeah, it's 0-1 loss, right? And so we have a similar notion of loss for regression, but 0-1 does not make sense, because you don't want to say, do you get the label exactly right or not? it's okay to predict the price of a share to be 24.5 if it's 24.6 or whatever, right? So how do we measure it? Speak loudly.
The L to norm of the error.
Yeah, L to norm, right? So you could measure squared error, right? So you measure deviations essentially. So you have a label you want to predict, you have its unknown value, so the y is the true label, and you predict f of x, and you care about how much does it deviate from the true label, right? And you can measure the deviation in many ways. One of the ways is the squared error, okay? And so in regression, in fact, this squared error, or actually the mean squared error, because x and y can be random, you want to be able to do well in expectation over any random draw of x and y, right? So we care about something like the mean squared error. This is one of the error metrics of interest. Of course, you can measure deviation in other ways, like you can measure the absolute expected value of the absolute value, that's another one. But we, for reasons that, essentially the squared loss is easy to optimize. Okay, it leads to a very nice convex function, and it's easier to optimize. That's why very often we talked about the squared error in regression. All right? Okay, so that's what's going to be our focus, at least for today's lecture. And we'll look at a bunch of regression algorithms, which means now we want our algorithms to be able to predict what the label is up to some deviation, a small deviation from it. Right? And we'll talk about, again, having training data, trying to come up with a learning algorithm that gives a prediction rule which you can apply to a new test point and predict its label up to certain deviation. Right? And we'll look at methods. We'll talk about linear regression and maybe regularized linear regression today. In next class, we'll talk about maybe polynomial regression, kernelized regression, and Gaussian process regression, which are more nonlinear versions of the nonlinear approaches to regression, I should say, just like you did for the classification setting. All right? So let's start with thinking about what's the optimal predictor, right? So optimal predictor is easy to define. Even for classification, we said it's the classifier that achieves the minimum probability of error, right? So here it's the classifier or the predictor f, which minimizes the mean square error. Of course, the problem is we don't really know what this distribution is over which this expectation is computed, right? And in the first class we said, well, we don't know the expectation or the distribution, but we have a training sample, right? And we use the training sample to get a glimpse of what that error should look like. So you can think of using your training data and just replacing this expectation with an empirical average over your training points, right? So you want to minimize the empirical error on your training points, xi's and yi's. These are given to you. So you could say, well, I want to now pick a classifier that does well on my, I don't know the true expectation, but I can compute the empirical expectation or empirical average over my training set. And I want to pick a predictor that does well on that. This is good. So you see that what we did was replace the expectation with the empirical mean. But is that enough? If you're keen, you will notice that there's another difference between the two expressions here. Anybody pick that out yet? So you'll notice that here I was saying, well, the best predictor, right? Minimize over all possible functions, pick the best predictor. Of course, none of this is possible, but I just mean to say that here we have the minimization over all possible f, and if you notice that now I actually put that the regression function or the predictor I'm trying to learn belongs to some class, which I call calligraphic f here. Okay? And why do we need to do that? Why do we need to now restrict, once we replace the expectation with an empirical mean, why do we need to restrict ourselves to particular classes? So think about what would be the solution if I did not have a particular class. Like I could force f to be linear, for example. That would be example of one class of restricted functions. What happens if I don't do that? Overfitting, right? Yeah. So we could have, first of all, yeah, I guess I just wanted to make this point that why does this replacing with the empirical mean make sense? Just because from law of large numbers, you know that the empirical mean converges to the true mean, right? So that's just to say why this would make sense. But yeah, now getting to the question of, well, why do we need to restrict our class of predictors? Because here's some training data. I have x's and I have y's, right? And if I just say pick the function that minimizes mean square error of this data without imposing any restriction on what functions I allow you to choose, you could pick anything arbitrarily wiggly, right? As long as it passes through, as long as it gets the labels of all the training points correctly, it's a valid solution, right? But somehow this doesn't seem meaningful. It seems like it is overfitting our training data. It's not going to generalize very well, right? Of course, that completely depends on the data you have at hand. The assumption here is we believe our data is sort of smooth. It does not vary in this very jagged fashion, which could be the case sometimes if you're trying to model solar bursts or something like that. Maybe you need a different model, right? So what class you need to restrict your functions to depends on what type of data you're modeling, what's your prior assumption about it, or what do you know about the application at hand. But for most applications, it makes sense that you can't hope to generalize very well unless your function is sort of smooth, right? So we expect that the true function maybe is something like this, and that's why we want to not allow very arbitrary functions that can minimize your empirical error or the training error, right? So yes, it leads to overfitting, and that's why we don't want to just consider the minimization over all possible functions. Okay? So we restrict ourselves to particular classes, which implies a constraint on what's the shape that we are trying to fit. Okay, so we'll talk about a bunch of these. We'll start with the class of linear functions, but then we'll also go to polynomial functions and then more general nonlinear functions. All right? So any questions on this? Fairly simple, yeah?
So what distribution does that expectation use with vector?
It's a joint distribution of x and y, right? So you believe that there's some underlying joint distribution of x and y. Your training data are drawn IID from this, and your test data is also drawn IID. Except that you're not revealed the label, you have to predict it for the test point, right? Yep. And that's why you can hope to get a glimpse of what that distribution is based on training data, because training data is drawn IID from it. That's the assumption. Yeah.
So you mean that you have variance on x and variance on y?
You have variance?
Yeah. So we have variance on x.
There could be, yeah. The x and y are random variables, right? So they have certain variance. That's true for any problem, even classification or everything we have talked about so far. Yeah. We are always modeling x and y as random variables, right? Yeah. Any other questions? All right. So let's talk about linear regression, where we restrict our class of predictors to now be linear functions. Okay. So what exactly do we mean by that? In the univariate case, where we have only one feature, it means we are only going to allow functions f of x that look like linear, essentially beta 1. There's an intercept term beta 1, and then you have a slope characterized by beta 2. Right? So beta 1 plus beta 2x, that's a simple linear form. This is for when you only have a single feature x. Right? More generally, you can have p features, x1 through xp. And again, to simplify notation, we can think of the first one as being 1, so we don't have to treat the intercept separately all the time, right? So we'll just call that as 1. But now you have as many coefficients. So beta 1 and beta 2 were the regression coefficients. That's what we call them. And now there are going to be p of them. So it's just a weighted combination of your features, really, right? That's what we are trying to do. And one of the things that's very helpful here is to be able to write this in vector or matrix form. Okay, so what we'll do is, instead of writing out this whole equation, we'll just call it x times beta, where x is a vector that contains all of your features, the p features, and beta is so x is a row vector, beta is a column vector that contains the p regression coefficients corresponding to each feature. Okay, and then we can just use this shorthand notation that f of x is x beta. That's our linear class. We only want to fit linear functions to our data. All right. Okay, so what happens when we do that? So if we are trying to minimize something like, again, the empirical error on our training data over all functions that are linear, which means they look like this. F of x is x beta, or in particular, the f of xi, I'll just replace it with xi times beta, right? And if we do that, then we essentially are trying to solve for, we can rewrite the minimization over f as the minimization over beta. Right? We can equivalently solve for beta, and then our final prediction will be just x times whatever beta we learn. Okay? So I can, instead of optimizing over this whole function f, once I've restricted it to be linear functions, I can instead minimize over beta, where I have substituted for f of xi times beta, which is the linear form. And the solution you get is now called least squares. right? Which makes sense. It's just minimizing the, so that's why it's the least, getting the least squared objective over your training data points, right? It's called least squares estimator. Okay, so again, it will be helpful to rewrite this in a matrix notation, or at least it will jog your vector and matrix calculus. So we'll try to do it that way. Of course, we can write it in this long form and try to work with that as well. But let's go to the vector and matrix notation, which is as follows. So I can take this expression. I want to minimize it over beta. And I want you to use vector calculus. So we'll write it as a, in the matrix or vector form as follows. And then we'll optimize it over beta. So why can I write it like this? So what are the ingredients here? Well, y is nothing. You had a bunch of labels. We just put all of those in a vector, right? So y1 to yn. The A matrix is just your input data points, right? So the first x1 is the first data point, xn is the nth data point, and each data point has p features, right? So that's where this denotes the p features corresponding to first training data, p features corresponding to the nth training data point, right? And it's easy to see that if I write it like this, a beta minus y transpose a beta minus y, you get back this. Everybody comfortable with this? Or do you actually want to see how you write it in the, how the matrix form works out to be same as this least squares form? Oh, everybody okay with that? Anybody who wants me to explain it? Okay, all right, so yeah, this is fairly easy. Just wanted to make sure everybody gets it. All right. Okay, so now we have this objective function, which is a function of beta, and we can write the objective function here, and you want to minimize it with respect to beta. So what do? We take derivatives with respect to beta, right? And so all we have to do is solve this problem. And there are essentially two facts about, oops, I just moved it. Yeah. There are two facts about matrix calculus that are going to be important. One is that we can, if we take the derivative of a linear function with respect to where both a and x are vectors with respect to the vector x, then you get back a. And you should notice that this is same as the derivative of x transpose a with respect to x, right? Because x transpose a and a transpose x are really the same thing, right? So this is one fact. And the second fact is that if I take the derivative of a quadratic quantity like x transpose bx with respect to x, so here x is a vector and b is a matrix, right? Then the derivative is actually b plus b transpose times x. Okay, so we'll use these two rules, and these are good rules to have on your cheat sheet, for example, for the exam. Then you can do this optimization fairly easily. All right, so what do we get? If we open this up, the quadratic term, we get beta transpose a beta, right, minus beta transpose a transpose y, minus y transpose a beta, and then plus y transpose y, right? So we are trying to take the derivative with respect to beta. What do we get for the first term? Just think of that a transpose a as the matrix B, right, here. And beta corresponds to x. So when I take the derivative, I get back, anybody? Yep, you get twice a transpose a, beta. Twice because b and b transpose here are the same, right? Okay, what do I get for the second term? And the third term, actually they are the same. If you realize that it's just a scalar term, really, right? Then now you can think of it as, say, for example, we look at the third term, then that is in the same form as a transpose x, right? And we are taking the derivative with respect to x, so we just get back the transpose of whatever multiplied x, so the transpose of whatever multiplied beta here. So you get back a transpose y. And you get twice of those because both of these are really the same expression, right? Everybody comfortable with that? And of course, the y transpose y term does not depend on beta at all. So you just have this. So it was fairly easy. We set it equal to 0 and at our solution, beta hat. Right? So it's almost tempting now to say that the solution is beta hat is just A transpose A inverse A transpose y, right? The reason I say it's tempting is because, yes, it's true that our solution satisfies this, right? So if you equate it to 0, you get, these are known as a set of normal equations, okay? But they essentially look like you have A transpose A times beta hat A transpose y. So the solution of this set of equations is your least square solution beta hat. And of course, you would say, well, why not take the inverse of A transpose A? If it exists, you can take it, right? So yes, if A transpose A is invertible, then your least square solution is just this, right? And remember again that betas were just your regression coefficients. These are the weights that multiply each input feature. So to actually get the prediction, you still have to take those weights and multiply it by the corresponding features of the test point to predict the label of that test point, right? So don't just leave the solution at this. If you have to predict the label is not beta hat. Those are just the regression coefficients. You still have to, of course, take your test point, right, and weight the features accordingly. All right, so what happens, well, first of all, when is A transpose A invertible? So do people remember when matrices are invertible? They have to be full rank, yeah. What's the rank of A transpose A? So we said we have n data points and we have p features. And just to remind ourselves, A was defined as x1 through xn, which means that it's all the p features corresponding to each data point, right? So it is a n by p matrix. So what's the rank of A transpose A? Okay, some people say p. Any other answers? Yes. So actually the answer is whichever is less between n and p. And how do you see that? A number of non-zero rows or columns. Well, it's linearly. So rank is the number of linearly independent rows or columns, not the number of non-zero rows and columns. Okay. So yes, it's the number of linearly independent rows and columns. And one way to see that is actually it's also the rank is equal to the number of non-zero eigenvalues of the matrix. Right? At least that's one way to see it. So how do you see how many non-zero eigenvalues it has? Well, let's look at A, and we can form its. This is just one of the ways. There are several ways to argue this, so you can pick your favorite way. One of the ways is to just look at the singular value decomposition of A. Let's write it as U sigma V transpose, right? Then what is A transpose A? Well, that's just U sigma V transpose, or sorry, V. It's the transpose of this, so V sigma, because sigma is symmetric. U transpose times U sigma V transpose, right? And U transpose U is, at least if you write it in the canonical form, it's just identity because eigenvectors are orthogonal. So you get back V sigma square V transpose, right? So the eigenvalues of A transpose A are the same as the square of the singular values of A. And how many singular values does A have? A is n by p. So the number of singular values has to be the minimum of n and p, right? The number of linearly independent rows and columns of A has to be less than the dimension, right? So number of non-zero singular values of A is less than the minimum of n and p, which implies that the number of, I'll just say non-zero eigenvalues of A transpose A is less than the same quantity, right? So, okay, getting back to when is A transpose A invertible? We know that its rank has to be less than the minimum of n and p. When is it full rank? When its rank is? What should be the, for A transpose A to be full rank, what should be its rank? P. Right? It's a p by p matrix. For it to be full rank, its rank should be p. But we know that its rank is less than the minimum of n and p. So it will only be full rank if p is larger than n. Or sorry, p is less than n. Yeah, wrong way. Yeah, if p is less than n. So if you have fewer features than the number of training data points, this is invertible. You are in the low dimensional setting, you have lots of data points, right? So then your rank is, the minimum of n and p is p, and your full rank. So you can invert the matrix and you can go ahead. So for small number of features or large number of data points, the solution can be known in closed form. But if you're in the high dimensional setting, which is almost always the case in any big data set, right? You have a lot of features. For example, we talked about images. You have, say, a brain scan of every person. There are very few subjects, so n is very small, but every subject is characterized by this very high dimensional brain scan, right, corresponding to as many, the dimensions are as many as the number of pixels in each image, for example. So you're in a very, very high dimensional setting. Typically, p is much larger than n, and you can't do this inversion, right? So what do you do then? So we'll get back to it in a little bit when we talk about regularization. But I just wanted you to, at this stage, understand that it's not necessary that this is invertible. So the normal set of normal equations are always satisfied by the least square solution, but you can only write the least square solution like this if A transpose A is invertible, which happens if you have lots of data points n larger than p. All right? Okay, and we'll get back to what do you do if it's not invertible. So suppose it is, suppose you do have a lot of data points compared to the number of features, then, well, you are done. You have a closed form expression, right? A was formed from your training data, just concatenating it together. Y was all the labels of the training data, so you can compute this, and you are done. Though even there, actually doing the closed form inversion of A transpose A might be expensive, right? When p is large, it could still be invertible. You could have a lot of data points, but still, if p is large, doing the inversion is not easy. So in many settings, you may actually not want to use this closed form expression, but you want to revert to something else, which is computationally more tractable to do the inversion, okay, or to come up with this. So for low dimensions, and even if you have a lot of data points, as long as the dimension is fairly low that you can compute the inverse, you would do that and use the closed form expression. But even if your p is less than n, but p is still large, computing this inverse is expensive, and so we will resort to what we know how to do, convex optimization, right? So we have to compute beta, which is the minimizer of this expression, and we'll note that this expression is convex in beta. It's a quadratic in beta, so it's convex, right? It looks like a bowl. And we'll just use our favorite trick, which is do something like throw any kind of optimization algorithm at it, for example, gradient descent, right? Which we know how to do. So here's our objective function, and we want to minimize it with beta, and realizing that the objective is convex in beta, so in 1D or 2D, it looks like a bowl. It's a quadratic. We can find the minimizer by looking at essentially moving in the direction of the negative of the gradient, right? Because now we want to move down the hill, so we want to move in the direction of the negative of the gradient, right? As opposed to maximum likelihood estimation when we wanted to do gradient ascent and go to the top of the likelihood function, right? So we do something similar. You initialize betas randomly, and then you update them, where at the next step, the regression coefficients are just whatever they were at the previous step, times moving a small step size, which I've written as alpha over 2 here. This could be your eta. The 2 just helps because it cancels something in the derivative. And this is just the derivative of your function with respect to beta. And we had actually already computed that, I believe. So this is right here, is the derivative of your objective function, right? So that's the gradient. We plug it in here. It's just A transpose A beta minus A transpose Y. And having the 2 here helped because now it cancels this 2 in the gradient. All right, so what is this update doing? If I rewrite it by pulling out the A transpose, it's saying that we are going to move the regression coefficients a little bit. How much we move, of course, depends on alpha, and how much, this is like, you can think of this as your prediction, right? With the current set of regression coefficients, x times beta was your prediction, right? Or A times beta is the prediction for all of your training points. So this is the predicted label using the current coefficients at the tth iteration and how well they match the observed labels for your training points. So you're just looking at that, and at the optimum, this should be 0, right? You should be able to predict very well. So this is getting smaller and smaller, right? And otherwise you're moving in the, as long as this is large, you're taking a step in the negative direction. All right, so it's just simple gradient descent now applied to this function. And how do you stop in practice? Well, you use some criteria, like either you fix the number of iterations for which you will run this gradient descent, or you check your gradient, and if it's small, then you stop there, right? So this is something you have already tried in your homework 1. All right, so any questions on this? But this is just another way to solve, to get to the least square solution by using gradient descent, or just throwing any optimization algorithm at it. Yeah.
You mentioned before that you couldn't invert the matrix when you have a small amount of data points. Can you still do this?
No, so yeah, you can't. You can do it, but it's going to be very, very slow, the convergences. That's why we use regularization. So we'll talk about regularization in a minute. Right. Because how quickly gradient descent converges depends on how flat or steep this bowl is, right, in different directions. And if you have fewer data points, then it can be very, very flat. So convergence can be very slow. So you would actually not want to do this. You want to use some regularization that we'll talk about shortly. Yep. But you can still do gradient descent on the regularized objective, and that will be good. Any other questions? All right. So then I also wanted to mention, you all know now what least squares estimate is, right? You're just fitting a line, and how you get the regression coefficients, we have talked about that. But you can also look at the least squares from a different lens. You can think of it as maximum likelihood estimation, actually. Okay, and how can you do that? Well, for that, we can actually go to this signal plus zero mean noise model. So we have some y, right? So these are our labels for our training data. And one way to get at this regression function is, or get this fit, is to think of y as being some function plus noise, right? Sort of intuitively makes sense. So if we buy into the signal plus noise model, where we think of the signal as being this linear function, right, and beta as being the parameters of this model, then now we can do maximum likelihood estimation under this model to find the right betas. And we'll see that under certain assumptions, that maximum likelihood estimate of the beta is actually the same as the least square solution. All right. Because I see people nodding, I'll ask, can you guess what those conditions are? Something has to be Gaussian. What has to be Gaussian? Exactly. Yeah. All right. So you all got it, right? So if you think of our think of x's as fixed, right, and epsilon, our noise, as just being Gaussian. So you're essentially what this says is your labels are being generated from this line plus Gaussian noise, zero mean Gaussian noise added to it. So if we assume that, which means that we can equivalently think of y as being a normal with the mean being this line and some variance around it, then we'll see that you do maximum likelihood estimation under this model, and your solution is actually the same as the least square solution, right? So we maximize the likelihood of our data for these parameters. Actually, just beta, that's what we care about. Sigma square is a nuisance parameter here. We don't necessarily need to estimate it. And you can show that it arrives at this. Actually, it's easy to see. Maybe we can do it quickly. So what we are talking about is the Mle estimate is arg max over beta. And we are just looking at the log likelihood here as before. So log of the likelihood, of course, all the data points are drawn IID. So we just have the product over I equal to 1 to n. And then what does the distribution look like under this model? Well, we said y is distributed according to this normal model, and x's are fixed. So we are just going to maximize this the Gaussian distribution here, which is, I think, d by 2 sigma. Like sigma here is really sigma square I, so I can literally replace this with sigma to the d, right? And then you have the e to the negative yi minus xi beta square over 2 sigma square, right? And once we write it in this form, you can see that now I can move the product outside the log. It becomes a sum of the log of this part. Does not matter. It's just a constant because you only care about what's the value of beta that maximizes this expression. We can throw out the part that's independent of beta, right? And we are left with just this exponential. So we are now trying to say argmax over beta, the sum I equal to 1 to n, log and e cancel, and we are just left with this quadratic term. Okay, and so that's same as trying to maximize the negative of that squared expression is same as minimizing the positive of that expression. Right? Was that too fast? Do people want me to go more slowly over it, or do you get it? So all we did was, for the likelihood, we write down this multivariate normal, right? And then the steps are just log of product is the sum of the log, right? Log of these two terms. The first term doesn't matter because log of a times b is log of a plus log of b, and the a part is independent of beta. You don't care about that, right, when trying to find the maximizer. So you end up with something like sum I equal to 1 to n log of e to the this term, right? And the logs and the e's cancel, so we are talking about maximizing negative sum I equal to 1 to n of yi minus xi beta square. Again, I can drop the 2 sigma square, that doesn't matter, right, because we are just finding the maximizer. All right, so maximizing negative of that is same as minimizing the least squares objective, and so we have shown that the maximum likelihood estimate is same as the least squares estimate. Any questions? So it's under this model that you're buying into a signal plus noise model where your noise is zero mean Gaussian. Under that particular model, the maximum likelihood estimate of beta under that model is the same as the least squares estimate, but not in general. Okay. All right. So now that we have talked about maximum likelihood estimation, what else did we study along with it? MLE? Something related? You can do MLE estimation or you can do map estimation. So why not throw map at it, right? So what if we did map estimation here? What would that entail? So in map, we maximized not only the likelihood, but the likelihood times the prior. And what was the prior over? It was over whatever parameters, right, of your model. And here the parameters are beta, right? At least that's the one you care about. Sigma square is a nuisance parameter. So we are going to put a prior over beta and say, what if instead of maximizing just the likelihood, we maximize the product of the likelihood and the prior, right? And that actually leads us to regularization. So why did we do map earlier and not just MLE? Like, for example, when you're talking about naive Bayes, because if you don't have enough data points, then your MLE estimate can be bad, right? That's where you bring in prior knowledge about what your parameters should be. We'll do exactly the same here. If you don't have enough points, if you're in the n less than p setting, you might want to regularize a little bit. And one way to do it is to bring in a prior information. All right? So now we'll answer the question, what if this is not invertible? Well, you do regularization. You assume some prior for your beta, p of beta. And now we are going to maximize the product of the likelihood and the prior, which in terms of log likelihood and log prior is just the sum of the two quantities, right? Okay. So what kind of priors can we assume? Well, one prior is just to say that your regression coefficients are, again, Gaussian with zero mean and some other variance, tau, right? That's one way. So this is saying that you believe your regression, most of your regression coefficients are small, and maybe they follow a Gaussian distribution, the remaining ones. Whether or not this is a good prior, again, completely depends on your application. You really want to use a prior that's motivated by your application. But in many settings, it makes sense to say that the regression coefficients are zero, maybe just for interpretability, if not anything else, or for storage, so that you don't have to store all your coefficients. You want some of them to be zero, or you want your model to be interpretable in the sense you can say, I can predict whatever output I want to predict. Say that we are trying to predict the age of people based on only these specific features are the ones that are relevant. Everything else has a zero regression coefficient. We don't really care, right? So it gives you an interpretable model as well. So that's why it might make sense to try to say something like this. And if we put this Gaussian prior in here, right, you can now think of this as just regularization. We have the least squares. The log likelihood is just like the least squares, right? We just discussed that. And now we have another term, which is a penalty term on beta. So you can think of it as a regularization of your least squares objective. And in fact, if you plug in this Gaussian prior, you get exactly the log likelihood prior, as I said before, is the least squares objective. And the log prior, which is the log of this Gaussian prior on beta now is just an L2 penalty on the norm of beta. So you're saying try to fit a linear model with regression coefficients beta, but make sure that the norm of those beta coefficients is not too large. Okay? And actually you should try to do this. It's a good exercise to actually plug in this P of beta here and try to figure out what this constant lambda, how it depends on. So there are two variances here, right, that will come into play. One was the variance under your maximum likelihood model. This was the noise variance. And tau is the variance of your prior. And you'll see that this lambda term sort of depends on them. But in general, you just pick some lambda or you tune it by cross-validation. That's what is usually done in practice. All right? So yeah, we really need a lecture on cross-validation now. I think we've talked about it so many times that, yeah, you should see it formally. So we'll get to it soon. All right, so this formulation, this regularized least square objective is known commonly as ridge regression. Okay, so you might have seen it before, maybe not from this map perspective, but that's what ridge regression is about. And you can do something similar to what we did for finding the maximum likelihood estimate here. Now we can find the map estimate under this model. And I won't do it here, but it's either you should do it yourself or it will be a good thing to cover in the recitation, or maybe it will appear on the homework problem. Okay? But you can see that now your regularized solution, the map solution, looks like this. So if I set lambda to 0, means I have no regularization, I get back my least squares solution. But if lambda is in there, then you have this solution. And why is it nice? It actually addresses our question of what if A transpose A was not invertible. A transpose A might not be invertible, but now that we have added some diagonal terms to it, it becomes invertible. Right? So this regularization essentially helps with the invertibility. And that's why you might want to do it. All right. So that's the map estimate. Any questions on this? Yes?
Sir, why does adding diagonal terms make it invertible?
Why does adding diagonal terms makes it invertible? What's an easy answer to that? Well, if you can look at your eigenvalues, I guess that's one way to do it. And you see that now whatever were the eigenvalues of this, you're sort of adding lambda to those eigenvalues. So whatever values were 0 earlier will now be lambda. So you're making more eigenvalues be non-zero. That's one way to think of it, so that your matrix is now invertible. I don't know if there's any other easy way to.
I think that's the best way. If you think of A transpose A as being factored as U sigma U transpose, right, then adding lambda I is equal to lambda, it's
maybe I can.
U transpose is equal to I, so you just pull the U's out to the side and add lambda to the sigma.
Yeah. Maybe I should write it just so you. So if again going back to the singular value decomposition, I can write U, or I guess we wrote it as V sigma square V transpose, right? And then, all right, yeah. Somehow, the alignment does not match up here. Yeah, but then I can just throw in VV transpose here because VV transpose these are orthogonal, right? These are eigenvectors. So now you can see that what happened was we have all the, I should have lambda I here, right? All of the eigenvalues here are now becoming lambda time, are being added, lambda has been added to them. So if they were 0 earlier, now they are non-zero. Right? So now your matrix can still be full rank and you can invert it.
Or what if there's a minus lambda?
You don't want to do that. So this is something you're adding in, right? The regularization term.
Oh, and the eigenvalues of a positive semi-definite matrix are all non-negative.
Right.
So you can't have the squares are all positive.
Right, I mean, they are squares, you can see that, right? So that's why they are positive, right? That's why you want to add a positive quantity to it. Okay. That's a good question. Any other questions? Yeah.
So this regularization model we talked about, though, is working under the assumption that the errors are normally distributed.
So if you study ridge regression, it does not necessarily assume that, but it has this map interpretation under the Gaussian model. Okay? Yeah. But in general, it can be, this regularization is used without making any assumptions.
This is actually a really good example. We make assumptions to be able to derive something, but sometimes what we derive will work under much more general assumptions.
Yeah.
And this is one of those cases.
Right. Yeah, that's a good point. Right? The algorithms we come up with sometimes work under much more general conditions than what we actually chose our models to be when you derive them. Yeah.
So, wait, so I'm sorry, does that mean then that if you don't have Gaussian errors, you're going to get a bias? Like is there some issue with assuming that it's Gaussian if it doesn't perfectly follow?
So you can, for ridge regression, you can prove things that are like the empirical risk minimization bounds that we showed for the perceptron, where worst case over all possible sequences of training examples, as long as there exists some predictor that does well, we're going to do not much worse than that best predictor. So that requires a bit more effort to prove, which is why we aren't proving it here. But you can prove something much stronger than what we just showed.
Right. And again, what you would want to do is actually the key is also setting lambda. As you get more and more data points, right, you sort of want to have lesser and lesser regularization. So typically the way lambda is chosen is that it decays as number of data points increases, right? So in the end, you are actually getting back your least squares estimate. Right?
Or even if lambda is constant, right, it gets overwhelmed as A grows.
It gets, oh yeah, right, you're right. So yeah, that depends on the normalization, but yeah, you're right. Yeah, right. If we have, yeah. But anyway, that's, yeah, I think you get the idea, right? Yes, okay. Yeah, more questions? So you can still use it. And in fact, what this is helping do is now your gradient descent will actually converge faster, right? Because now it's not in all the directions that were very flat are now not so flat. Okay, so you can still do that, yeah. And you might want to do it again if this is big, right? Yeah, all of these are great questions. Anything else? Okay, so let's talk about one other regularization that has gained a lot of popularity. So here we talked about this regularization based on the Gaussian prior. We can also use I think we talked about this, that it biases, using a Gaussian prior with zero mean biases the solution to be small betas, and we talked about why that might be useful to have a few regression coefficients that are zero. So to sort of specifically focus on that, we can actually use another prior which penalizes even more heavily the non-zero betas, and that's known as the Laplacian prior. So we can assume that, so first of all, beta is actually a vector, so there are p regression coefficients, and we can assume each of them is IID Laplace with zero mean and some parameter t, the Laplace parameter, and this is how the Laplacian looks like compared to the Gaussian. So you can see that it's penalizing, at least if I normalize maybe the peaks, it's penalizing the non-zero values even more. That's the way to think about it, right? And so if we use this prior, then what ends up happening is, if I plug that in here, log of this term, right? And this is over, we're assuming it's over each coordinate of the regression coefficient, each beta I is like that. Then what we end up with is now just the sum over I of the absolute value of beta I. That is your regularization, right? Which is also known as the L1 norm. So you just end up with a different norm in which you regularize your beta coefficients. It's the L1 instead of the L2 norm, and this is known as the lasso, and it has really, or in general, like I guess penalizing using L1 norms has become very, very popular, particularly in high dimensional settings, because it actually forces the solution to be even more, not only that it forces some of the betas to be small, it actually forces many of them to be zero and the others to be non-zero, which leads to, once again, an interpretable model and also savings when you're trying to store these regression coefficients, for example, in high dimensional settings. Right? So prior belief that beta is Laplace, again, biases your solution to not only small betas, but actually betas that can be exactly zero. Many of the regression coefficients can be zero. So maybe I thought, like, since this is so popular, let's look at a little bit more at this comparison between the two priors and understand what's going on. So what we have is essentially the least squares objective with some penalty, whether the penalty could be either the L2 norm or the L1 norm of beta. Okay? So once again, if you didn't get that, the L1 norm is just defined as just the sum I absolute value of beta I, whereas the L2 norm is the standard Euclidean norm. Right? So the only difference is these two penalties, right? And what's the effect of them? One way to understand it is, and if you read the classic paper on lasso, you sort of see pictures like this. And what this represents is as follows. So first let's ignore the penalty, right? Then we said we just have the least squares term, right? And least squares term is, if I look at it as a function of beta, right? So we are plotting it, you can see the betas are the axes. For example, you only have 2 of them, just so that you can visualize it. I can't draw in 3D or 4D very well. But yeah, in 2D, if you have 2 regression coefficients, then your least squares objective is a quadratic in betas, right? So it's a bowl-shaped function. And if I draw contours of that bowl-shaped function, so all the beta values for which the j of beta, the least squares part, has a constant value, then you end up with concentric circles like this, right? You can imagine these are the contours, level sets of a bowl-shaped function, right? Which centers at the least squares estimate. So beta hat is at the center. So that's what you get if you don't have. So you're essentially somewhere, you initialize your, say, gradient descent somewhere at random, and then you move down the gradient until you reach the least squares objective if you don't have any regularization term. Now we have a regularization term, so the objective is not only to move towards, so if you start somewhere, it's not only pulls you towards this solution, but you're also pulled towards another solution which optimizes your second term, the penalty, right? And what is the second term? For example, for ridge regression, it looks like just the L2 norm square, right? So when is that L2 norm, what are the contours of that L2 norm squared ball, right? So if I want to draw all betas for which norm beta square is constant, you just get concentric circles around the origin, right? Does that make sense? Because for norm 0, you just get the 0 vector. For smaller and smaller norms, which have the same value of L2 norm, you just get concentric circles here. So now you can think of these two functions, and you're sort of trying to balance them out. So for your solution, say your solution was some beta star, a particular value of the least square objective equals lambda times the L2 norm error, right? So basically it's about where one particular curve, one particular contour intersects another particular contour of this function, right? Where do their contours intersect? That's where your solution is given. And depending on the value of lambda, you could be looking at this particular contour, or you could be looking at a larger contour and where that intersects another contour over here. Where that intersection happens kind of depends on what lambda is, right? When lambda is 0, you're completely pulled towards this solution. And when lambda is very high, you're pulled towards the 0 solution here. Otherwise, you get something in between. All right? So that's what happens with ridge regression kind of penalty. What happens with the lasso penalty? If you look at your least squares objective remains the same, so we'll still draw similar bowl-shaped contour curves, right? But what happens to this, this set? Now, instead of being an L2 ball, it's an L1 ball. And if you look at all betas for which this L1 norm is constant, it actually looks something like this. Okay, so it has this kind of a diamond shape. And the nice thing about that is now, here where the intersect could be anywhere, right? And the solution does not necessarily have any of the betas as 0. It could be small, but it's not necessarily zeros. Here, very often, it hits at one of these edge points, because it's a diamond-shaped ball. It's a spiky ball, so you have some edges sticking out in some sense. And they tend to intersect at such locations where one of the beta, your solution, if it happens here, has one of the directions completely 0. Right? And ideally, you would want this ball to be very, very spiky. Right? You would want this ball to be, actually I think I have it here, be something like this. And the reason I mentioned this is because L1 penalty is used all over the place now. Like last 10 years I've seen like tremendous use of it. So it's an important thing to know. And even if you don't get this, you can go read some papers. We can put some pointers to that. But yeah, so I was talking about, like, ideally you would want this ball to be very, very spiky. So you literally are guaranteed to hit only, the solution only happens when one of the betas is 0, which means either over here or over here, right? So you would want the ball to be like this. And you can get that by putting an L0 penalty. So instead of the L1 norm, you can put an L0 norm on your objective. But then the issue is you're trying to maximize, or minimize, I guess, the least squares objective plus this penalty. And the penalty with L0 norm is no longer convex in beta. Okay, so beta 1, the L1 norm is sort of a trade-off in the sense it's still convex, but it's as spiky as you can get while being convex. Okay? So it's still a feasible, a computationally fast optimization, but it leads to this sparse solutions where some of your beta coefficients can be exactly 0. Okay? So I hope that provides some intuition into why you would want to do something like the L1 norm. All right, so I think, yeah, we sort of talked about this stuff earlier. So any questions on this? Oh, so yeah, I should have defined that. So L0 is just saying the number of non-zeros. So it's, you can write it as 1 if that coordinate is non-zero and 0 otherwise. So it's just counting how many non-zeros there are. Yeah, and that's why it looks like this, because anything which has only this coefficient non-zero, that's where those vectors lie, and anything which has the other coefficient being non-zero lies along that line. So it looks like a cross, essentially, all the vectors with constant L0 norm.
Go back to last time.
Sure.
Yeah, when you do the summation, usually you have a bias term in the question. So
when I do the summation,
yeah, for the cost function. So usually you have a bias term in your.
By bias, I guess you mean the constant term that was up front, right? Yeah, but that we don't care about because we only care about not the minimum value of the function, but the minimizer. That's what the argument is here for. We care about what beta minimizes that. And so what beta minimizes, or what x minimizes, say, 2x, is same as the x that minimizes 2x plus 3, or 2x plus 4. Any constant term that does not depend on your minimizer, you can ignore.
I think he's talking about like the intercept weight, right? So if you
Oh.
intercept weight in your regression or in your perceptron or your support vector machine, right, you can always join a constant column to your feature vector.
Right.
That's something that Aarti mentioned earlier in
Yeah.
this lecture. For almost all of our derivations, we're going to just assume that if you wanted a bias term, then you made sure that one of your features is 1. Right? And that's actually, from the point of view of a software API, a really good way to do it as well. The user gets to decide whether they want a bias term by deciding whether to have one of their features be constant. Right? This was something that caused a bunch of confusion in some of the homeworks, right? That a lot of people thought that you had to force a constant term to be present. And that's not usually a good idea to force it to be present, because the user will decide and will tell you by just giving you a feature vector that has a constant entry in it.
Right.
When
Yeah.
you do the regularization, you don't penalize the weight on the function.
That's a good. So that's optional.
Right.
You can or you cannot, and do you want to?
Yeah, I don't know too much to say, but yeah, exactly. You can choose to penalize it or not. It's really, so yeah, in terms of interpretability, it does not buy you anything. But you might want to penalize it just to say, do you want a model in which the intercept can be very small? Mm-hmm. Yeah, is there any, right?
Yeah. I mean, like, for example, so the question is whether you should include, like, the sum of the squared intercept term in your L2 penalty, right?
So if x1 was all 1, the constant feature, then should you penalize beta 1 here or not?
Right.
I guess that's the question.
And for example, in a support vector machine, it makes a geometric difference in how you interpret the weights, right? There are it's not uniformly better to do it one way or the other. It basically depends on characteristics of your data. For example, a lot of the time people will center their features, right? So like mean subtract their features, and then there's often very little value in allowing a very large intercept parameter in that case. So you might as well penalize it and make things different, make things simpler. If you at the cost of some notation, right, you could make yourself a special norm that penalized the intercept term less and regularize with that norm. But again, that would just make the slides more cluttered, so we're not going to do it here.
Yeah, but I guess it's an important point to keep in mind is that one of the features can be different in the sense it's this constant feature that the user can input. Right. And you might want to treat its corresponding coefficient differently.
Right. I mean, general, all
Usually
of your
people.
features might require different amounts of regularization.
Right, yeah.
And our slides could get decorated with
Yes.
tons of notation.
So you could do sum I, lambda I times norm of beta I, absolute value of beta I. So yeah, you can make it as complex as you want, but then you have as many tuning parameters to play with, right? Yep. Good question. Again, any other questions? All right. So let's move on to, I think actually that's what I had on linear regression, but we can start a little bit about nonlinear regression also. But just to summarize, for linear regression, we talked about least squares estimator. We said that it has the least square estimator has to satisfy the normal equations. In some cases, it is also invertible. You may or may not want to actually do the inversion. You can resort to gradient descent to solve the problem. And we also talked about its probabilistic interpretation as a maximum likelihood estimator. And we can equivalently put a prior on your regression coefficients and make it a map term, make it a map problem where it's essentially like regularizing the least squares objective, right? And we in particular looked at two forms of regularization based on priors, the ridge, which led to ridge regression and the lasso. And both of them are actually used a lot, ridge regression being more traditional and lasso appearing more in the last several years. All right. So okay, so we'll start with, I think we should do a little bit of polynomial regression and regression with nonlinear features, and then we'll get to kernelized and GP regression next time. Okay. So what's the idea with polynomial regression? Well, we fit a line to our data, but why restrict ourselves to a line? We can fit polynomials, right? That's the simplest next extension you can think of. And so how would we do that? Well, let's first think of the case when we only have a single feature, right? If you have only one feature, then we can form a polynomial by just allowing for, so we have again our intercept term, we have that feature, which is the linear part. So in the linear regression case with one feature, we only had the first two terms. But now we can throw in higher and higher order, or higher and higher degree terms, right, that include that feature. So we can use x squared, x cubed, and all the way up to whatever degree you decide. You can decide to do up to m degree polynomials. And then it looks like this. Of course, if you usually have more than one feature, and then it gets more complicated because you can, if you have two features and say you want to do a polynomial of degree 2, right, then you would have x1, x1 square, you will have x2, x2 square, and you could also have x1 times x2. That's another degree 2 term you can include, right? So you can imagine as you're getting more and more features, this feature set sort of explodes, right? How many terms you want to include? Yeah, question? No? Okay. Right. So what we can do, at least for the one-dimensional case is easy to see, is now you've built this x, or I think we were calling it A earlier, this feature vector, which will consist of all of these transformations of your original variable. And you will have a corresponding set of regression coefficients corresponding to each of these. So you can think of it as if you're redefining your feature set to now include these higher and higher powers, right? And again, you can put those into your, actually, there's the A matrix, because I guess A is the instantiation of X for all the data points, right? So we get the terms corresponding to the first training data, this nth training data point, and so on. And that's our A. And we can again still write it as a linear regression, right? So the framework is still linear. We are modeling f of x as x times beta, right? And we still get the same solution. You can use all of the same tricks, except that now your A matrix or the X matrix of interest has all these pseudo features based on powers of the original features that you have put in. Okay? And as I mentioned, like if you are doing the multivariate case, then you have not only, so in the multivariate but degree 1 polynomial, which was the line, linear regression, you only had the first set of terms, just the first line here. But now we get all these terms, like for quadratics, we get xi times xj's, right? So we get xi squares, xj squares, xi times xj. If you are running up to third degree terms, then we have xi times xj times xk for all of them, and so on, right? So you get the idea. But you can still put everything into this big X or this big A matrix and still treat it as linear regression, where you have just transformed your features, or you've expanded that set to include these more possibilities. Right? So is that useful? Sure, you may not expect your a prediction to be very linear. For example, like Jeff showed the example of that stock market trend prediction. You certainly don't want to fit a linear curve there. So you want to do something more non-linear. But at the same time, the more features you throw in, the more complex you are making your function, right? So here are some examples of putting in or doing fits. Actually, it's not coming out very well. There are data points here. I don't know if you can see them. And these are just fits of different polynomials. So the true regression function is actually from which the data was generated is actually the blue curve. And the data was generated as this curve plus Gaussian noise with some small variance, which you sort of don't see here, but hopefully you'll be able to see on the slides. And then you're fitting different polynomials of, you can fit a polynomial of order 0. I guess degree and order are different. So you call a polynomial of order k has degree up to k minus 1, okay, which is the power, right? So we can fit a constant, or we can fit a line, or we can do higher and higher order polynomials. And higher order polynomials sort of get more wiggly, so you can do a better approximation to your underlying set. As you can see here, this third order polynomial seems like a better fit than the constant or the linear one in this case. But as you get to higher order polynomials, you see that actually if you zoom in on this part, you're fitting this curve pretty well, but then you are incurring a large bias because at other places you could be this curve, it's going up and down, but it can have lots of variation, and so you actually end up with a bias. So there's and we'll talk about sort of bias and variance also a little bit in the next class, where you will see that as you use more and more complex models, you're able to reduce your bias, but your variance means if I give you now a different set of training data and still fit a k equal to 7 model, is your fit very stable? And you will see that it actually varies a lot. It's not going to be very stable the higher the order of the polynomial that you'll use. So you are getting a better fit, but it changes a lot depending on your data instance. So you're going towards lower bias as you increase the degree of the polynomial, but you're increasing the bias. And so your overall error, we'll see that it can actually be decomposed into a bias and a variance term, and you really want to be balancing the two. That's what model selection is all about. You want to pick the right order model so that you do a good fit, but your estimate is also quite stable. Okay, right. Yep, that's telling me to close up soon. All right, so so that's what, as I said, we'll talk about picking the right order. It's again a model selection problem. You can do something like cross-validation, but we'll also talk about other methods later on. And let me mention one last thing, which is, why only restrict yourself to these transformations of your variables in polynomial terms, like x square and so on? You can think of building up any nonlinear feature set, right? So you can say, I'll just write a regression coefficient times something, which I'll actually now call fees. So it's taking your original features x and coming up with whatever nonlinear features you care about, right? So for polynomial case, it was constant, linear, quadratic, but you can be creative and build up e to the x, log x, 1 over x, sin x, whatever fits your data. You can literally come up with those features and put those into your, again, the big A matrix and work with those. But of course, now you're exploring the complexity of your space. And in some sense, that's what we are going towards here is you can ideally have infinite dimensional feature, right? And that's what you actually did in kernel SVMs and the kernel perceptrons, right? But then you can resort to the kernel trick. So that's what we'll talk about a little bit next time, about how you can take these infinitely dimensional feature vectors and still be able to do regression with them using the idea of kernels. Okay, and also Gaussian process regression. So I think that's all I had for today, but yeah, we'll continue on this next time and talk about the kernelized version.